Truck front panel. The goals and objectives of this case study are to examine the vibroacoustic performances of 4 different designs of a full-size truck front dash panels and evaluate the feasibility of using laser-assisted reconstruction technology to identify all vibroacoustic characteristics of an arbitrarily shaped dash panel. The input data in this case included the normal surface velocities measured at a few surface points and a few acoustic pressures. The former is used to reconstruct the normal surface velocity distribution over the entire surface, the normal surface acoustic intensity, and the time average acoustic power. The latter is used to validate the reconstructed acoustic pressures. The output includes all vibroacoustic information for a vibrating structure, for example, the normal surface velocity distribution over the entire surface, operational deflection shapes at all resonance frequencies, the acoustic pressure, and the normal acoustic intensity distributions over the entire surface, the time averaged acoustic power, sound transmission loss, sound transmission paths, dimensionless structure damping ratio, etc. Tests were conducted in a typical industry setting using a coupled semi-anechoic chamber and a fully reverberation chamber. The truck dash panel was mounted on a wall through a fixture that separated the semi-anechoic chamber and a fully reverberation chamber. A laser vibrometer was used to measure the normal surface velocities at some discrete points that were accessible to a laser beam. Sound viewer was used to measure the acoustic pressures at a finite number of few points. The overall setup was very simple and data acquisition was very straightforward. Once these data were taken, all vibroacoustic characteristics of the truck front dash panel were obtained through reconstruction. Shown here are the comparisons of the reconstructed and measured spatially averaged normal surface velocity spectra for 2 different designs, namely panels number 1 and 2. Results show that excellent agreements were obtained. Shown here are the comparisons of the reconstructed and measured spatially averaged normal surface velocity spectra for panels number 3 and 4. Once again, excellent agreements were obtained. Here are the comparisons of the reconstructed and measured ODS for panel number 1 at the first 6 dominant resonance frequencies. Now we show the comparisons of the reconstructed and measured spatially averaged acoustic pressure spectra for panels number 1 and 2. Results show that excellent agreements were obtained. Similarly, excellent agreements were obtained between the reconstructed and measured spatially averaged acoustic pressure spectra for panels number 3 and 4. Next, we reconstruct the spatially averaged normal surface acoustic intensity spectra for these 4 panels. These results will indicate the performances of sound transmissions through these panels. Once the normal surface acoustic intensity is reconstructed, we can calculate the time average acoustic power and determine STL values for each panel. We can calculate the dimensionless structure damping ratio of each panel as well. Now let us examine the performances of these panels by looking at the STL spectra. Results show that panel number 1 allowed the most amount of sound transmission, especially at the mid to high frequency ranges. Panels number 3 and 4 exhibited better sound transmission loss performances at the mid to high frequency ranges. Finally, let us review sound transmission paths through these panels. This is the most important piece of information. Typically, engineers rely on sound transmission loss of a panel to assess its noise reduction performance. This information is important but insufficient because there is no way of knowing where sound gets transmitted through a panel, which makes further improvements impossible. Shown here are sound transmission paths for 4 panels at the first major resonance peak, 96 Hz. Results indicate that panel number 1 allowed the most amount of sound transmission on the left side. Panels number 2 and 3 are better than panel number 1, and panel number 4 allowed the least amount of sound transmission at this frequency. At 125 Hz, panel number 1 allowed a significant amount of sound transmission through its center portion, while the other panels fared much better. At 146 Hz, panel number 1 allows sound transmissions at the left and center to the left portion. Panel number 2 allowed a significant amount of sound transmission at the left side. Panels number 3 and 4 were much better than panels number 1 and 2. At 160 Hz, panel number 1 allowed a significant amount of sound transmission at the center to right portion. The other 3 panels were much better. In conclusion, SoundViewer enables one to identify all vibroacoustic characteristics of arbitrarily shaped vibrating structures. Test setup is simple and measurements are easy. Output from SoundViewer are comprehensive, including ODS, dimensionless structure damping ratio, sound transmission loss, etc. In particular, SoundViewer enables one to identify the precise locations through which sound is transmitted. This information allows engineers to come up with a direct and effective measure to plug sound transmission. The insight into vibroacoustic characteristics gained by SoundViewer cannot be matched by any existing technologies. Thank you for your attention. For more information, please contact Dr. Sean F. Wu at seanwu@signal-wise.com.